Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 57 of the course Theory of Computation. This is also the beginning of week 12, which is the last week of this course. So far we have seen automata theory, we saw PDAs, NFAs, DFAs, etc. Then we saw computability theory, and then over the last couple of weeks we have been seeing complexity theory. To be more specific, we have been seeing time complexity. Over this last week, in the remaining time that we have, we will briefly cover space complexity, right? So just like time, space is also an important resource when it comes to like assessing how computation performs, right? So it is also a resource that we are bothered about when it comes to computation, right? So space complexity is about understanding or classifying problems based on how much space they require, right? So first of all, let's define what is space complexity, and then later we will see complexity classes based on space requirement, and then we will see different problems, computational problems, where they get placed, in which complexity class, how much space they require, etc. Right? So space complexity is given by a function just like time complexity, right, where the function indicates a maximum space required by the, just one second, I think they will get the color right here, the maximum space required by any input of that length, right? So just like time, instead of maximum time required, we are saying maximum space required. And for a non-deterministic Turing machine, it is the maximum space used by any branch of computation over all the inputs of the length n, right? So in a non-deterministic Turing machine, it is the maximum over all the branches of computation, right? So this is similar to how we define time complexity, but just that we are now measuring space instead of time. But before that, the notion of time, notion of time was rather well defined, right? So we just took time to be the number of steps, right? But what is space, right? So one natural thing to like interpret space can be the following. Like we look at how many like over all the tapes, how much space is being used by the Turing machine. So let's say it's single tape Turing machine, right? Which means the input is only on one tape, and the input is on one tape, and that's the input tape, and the work also gets performed on the same tape. Whatever we want, we do it on that tape, right? As we said, a single tape is equivalent to multi-tape, etc. Now the question is, what is the definition of space used, right? So one possibility is that, let's say the input occupies the first n cells, right? So n is the length of the input, and then as part of the computation we use some extra space, right? So the total space will be wherever the head accessed the tape and wherever it modified, etc. So this is, suppose this is the red and the blue part, this entire part is the space used by the Turing machine during the course of the computation. So it's, one may imagine that it's a convenient thing to assume that the space used is the number of cells on the tape. This is fine, but there is a small issue, right? The small issue is that now by default the space used is going to be at least the length of the input, right? At least n, right? The space used is, by this definition, the space used cannot be less than the length of the input, right? But this is in a way it is penalizing us, right? So just because the input is long doesn't mean that we should be using that much space, right? There are problems where the extra space that we require may be small, right? So what we should be charged for is the extra space, not really the space on the input. But sometimes it may get messy because maybe instead of using extra space, I just modify the input and get what I want. So now it's not clear how to like define what is allowed and what is not allowed, right? So the problem here is that, again, the problem here is that this model of measuring the space requires us to, or forces us to, forces the space usage to be at least the length of the input always, and we don't want that. So we want another model where we can get a more nuanced or more clear picture of how much extra space is needed. Okay, one small point of caution here. In this week, some of the presentation that I am going to do is going to be slightly different from how it is presented in SIPSR. For instance, in SIPSR, I think this definition comes later during one of the reductions, but we will just stick to what we are saying in these lectures, right? So I'm just saying that there is a small difference in the way the things are presented in SIPSR and in these lectures, right? Okay. So as I said, this model has an issue because there are problems which require only sublinear space. Sublinear means lid low of n space, right? Like let's say log n space or square root n space. But then this model will force us to use at least order n space, right? So we will change the model, right? The model is the following. Then this model will be more accurate and more faithful in terms of how much extra space is required, right? So we will consider a 2-tape Turing machine or a 3-tape Turing machine based on what is the goal of the Turing machine, right? So 2-tape or 3-tape. So I'll tell you why 2 and why 3. So there is a Turing machine and the input is on a read-only tape. So the input is presented and you cannot modify it. It's just presented there, right? So you cannot modify it. You cannot work on the input, right? And there is a second tape which is the work tape, right? All the work happens here, right? So the work tape is read as well as write. You could write something here, you could edit here, you could modify, you could overwrite, you could read. All of that can be done, right? So this is where the work really happens. And if it is a decision Turing machine, a Turing machine that says accept, reject, then we only have 2 tapes. If it is a computational Turing machine, if it's a Turing machine that computes a function, let's say it takes x as input and it has to compute some function on x, let's say it has to compute x squared or x cube. In that case alone, we need a 3rd tape, which is the output tape, right? So if it is a computational function or if it's a function computing machine, then we have an output tape, which is a write only tape. So again, we want it to be write only because we don't want it to be used for any work, right? So you just write something and we are not going to be able to edit it or read it, even read it. So we are just going to be write only. So some place where you write and forget it. And maybe this space will be used by some other machine or some other thing to access it, right? As far as this Turing machine is concerned, we just write and forget, right? So at the end, we want the output to be written here. So 3 tapes if it is computing a function. If it is a yes-no problem that the Turing machine is answering, only 2 tapes. Once again, the input is in a read-only tape. We are not going to be adding anything more. The work tape is a read-write tape, and the space that we actually call to be the space usage of the Turing machine is the space in the work tape. So how much of the space in the work tape is used, that is the space requirement of the Turing machine, right? So over all the inputs of the same length, what is the maximum space used? That is the space used in the work tape. That is the space complexity, right? So maybe I'll just write that here. Space used by the work tape. Space used by the work tape is what counts towards the space usage. Okay. So now the definition is clear. We have an input tape which is read only, work tape which is read write, and output tape if necessary, if we are computing a function, right? And the space usage is the space used in the work tape. So now it is clearly possible to use, let's say, log n space in the work tape, right? It need not be as big as n. In fact, we'll see examples where we use less than order n space, right? So now let me define complexity classes. This is analogous to d time of fn and n time of fn, which we defined in time complexity, right? So similar to them, we have d space of fn and n space of fn, right? So d space of fn is the set of all languages that can be decided by an Fn space or OFN space deterministic Turing machine, right? So deterministic Turing machine, that's why it's called D space. And N space is the set of languages that can be decided by an Fn space non-deterministic Turing machine, right? So this is D space Fn and N space Fn. This is just like D time and N time, but just analogously defined for the space. And one more point is that in the textbook they use the name space of Fn. So here I am just using D space just to kind of emphasize that it is deterministic, right? So let's see some problems, let's see some computational problems and see how much space they require. So one is 3-sat. So as we know, it is an NP-complete problem, right? So we have variables, we have Boolean formula with clauses and variables. So you have some clauses and the formula is the AND of these clauses, where each clause is the OR of 3 literals, right? So let's say x1, x2, etc. be the variables, L variables and K clauses. We have already seen many algorithms, but let's see one more algorithm. So we want to show that it is in D space N, meaning deterministic Turing machine, right? Deterministic, not non-deterministic, that uses order n space, ON space, right? So if you remember, it was NP complete. We don't know a D time N algorithm. We don't know that if it can be done in D time N. We also don't know if it can be done in D time N square, N cube, N power K for any constant K. We don't know if it can be done in D time N power 1000, right? For none of this is known, because such an answer will settle the P versus NP question. But here I am saying I don't need N square, I don't need N cube, I don't need N power 100. I just need N space or ON space to decide on 3-sat, right? And using a deterministic Turing machine, right? So the algorithm is fairly straightforward, right? Something that we have already seen. So basically we just try all the 2 power L assignments. So you could have a counter, right? So you could have a counter something like this. So initially it is all zeros, then it counts up, right? Then it keeps counting up, right? And so on, and finally you reach till the all ones, and this counter corresponds to the assignments. So this will be an L bit counter because there are L variables, and this counter will go from the all zeros to the all ones, meaning all false to all true assignments. So there are 2 power L assignments that it counter cycles through, and for each counter for each assignment we just evaluate the formula. So let's say for all zeros we just substitute all zeros in the formula and see what it evaluates to. So it's fairly straightforward, right? Each clause you evaluate whether it's true or false. If all the clauses are true, we say the formula is satisfied. If any clause is not true, we say the formula is not satisfied, right? So for the counter we need L bits, right? Because it's an L bit counter, and to evaluate the formula for a specific assignment, you can just look at each clause and see whether it is true or not. So maybe some constant, some 3-4 bits of extra space may be enough, maybe 5 bits, at most 10 bits, right? So given that it's a 3CNF form, you just evaluate a counter and see whether it is true. If it is true, you continue. If it is not true, then you can immediately say that this is not a satisfying assignment, right? So you just need to have the 3 assigned values for the literals in the clause, right? And at the end we accept if there is some assignment that satisfies the formula. If you cycle through all the assignments and none of the assignments satisfy the formula, then we reject. So that is the accept and reject condition. So we accept if there is some assignment that satisfies this. We reject if after cycling through all the assignments we don't find any assignment that satisfies this, right? So it's a fairly straightforward approach. But then the space requirement is surprising, because here we need only L bits for the counter and here it's in constant extra space. So all that we require is order L space, right? So L plus some constant, which is again constant, which is also which is also ON, where N is the length of the input, right? So usually N means the length of the input. So space required is ON, right? So that is so it's a deterministic linear space machine that can decide 3 set, right? So this is quite surprising, right? Forget linear, we don't have quadratic, cubic, like n power 100 algorithm for deterministic algorithm in terms of time, right? That decides that. Here for in the space bounded domain, we have a linear space algorithm. So the thing is that this takes a lot of time, right? So we are cycling through all the possible assignments, but then we don't need space. We are just cycling through assignments and testing each one of them. So it takes time, but not much space, right? So this is one indication that the space seems to be more powerful than time, right? We are able to do more things in the same space than we could do in the same time, right? Next is palindrome. In fact, we had seen a linear time algorithm using a two-tape Turing machine. Linear time deterministic algorithm using a two-tape Turing machine for palindrome. Let's see how much space we require, right? So let's say the input is written in the tape, right? So let's say 1, 2, 3 up to n, and the input is x, right? So we first check the first bit x1, and then we check the first symbol x1, and then we check the last symbol xn, right? And see if they are the same. If they are not the same, we immediately reject. Otherwise, we continue. Then we check x2 and xn minus 1, x3 and xn minus 2, and so on till we get to the midpoint. Right? So that's a very simple, straightforward algorithm. You reject if any of these pairs are not equal. You accept if you don't reject till then, right? So very simple, straightforward algorithm. How much space is required? The only space required is to maintain this counter that you are in position 1 or position n or position n plus I minus something or position I or whatever. So this counter I we need to store, right? We need to also calculate n plus 1 minus I. So these two things we need to store. And then we need to remember xi, which is a single symbol, when we go to xn plus 1 minus I, right? So basically we need to remember I, n plus 1 minus I and xi, and then go to xn plus 1 minus I. So I is a number that is bounded from 1 to n, right? N plus 1 minus I also is in the range 1 to n. So all we need is log n bits to store this number. To store I and n plus 1 minus I. And xi is a symbol, so it depends on the alphabet size. So if it is binary, we just need 1 bit. If it is decimal, you may need 4 bits to store xi, right? So but it's constant because the alphabet is fixed for the input alphabet, right? So it's not variable based on input length or anything. So this requires log n, this requires log n, and this is constant. So the overall space required is just log n space, right? So the overall space required is log n space. Again, now we are seeing another instance where palindrome, which required order n time, now only requires log n space, right? So we are seeing that it is significantly lower space, right? We took SAT, which required exponential time, like we don't know of any sub exponential algorithms for SAT. Now we could solve it in order n space, and palindrome, which we require order n time, now can be solved in log n space, right? So here we have two problems which can be done much better in terms of space, right? But not all problems are like that. There are some problems which require space which is of similar order, right? But in general, space seems to be more valuable or more powerful resource than time. If you are given the same amount of space, you seem to be able to do more than what you can do with time, but it's not clear, right? We are just talking on the basis of examples. Now let me define some complexity classes, right? Which are like we define P and P, etc. in the case of time complexity. So the complexity classes are L stands for log space, and NL stands for non-deterministic log space. Okay. So log space means it is the set of all. It is actually D space of log n. Right. So actually palindrome is in L. Right. So it is just the letter L, which stands for O log n space, and NL is the non-deterministic equivalent of that. It's the same amount of space but with non-determinism. And then we have, so notice that now in the case of time complexity, this log n space, log n time, etc. is not really meaningful, because just to read the input you need n, like you need to go through from the first location till the nth location. So just to read the input requires n time. But whereas in the space, that space is not being counted, right? The space where we use to store that input is not counted. So we can actually do meaningful things with sublinear space. This is not really, usually not possible in time. Like you could do some simple things like, there could be simple problems where you only look at couple of leading symbols and then decide. But in general, it is not very interesting to look at complexity classes or computational problems which require sublinear time, right? But in case of space, we have L and NL, which is log space and non-deterministic log space, right? So palindrome is in log space or palindrome is in L. So I am just explaining why there is a log space but not a log time. So now the third thing is, with respect to or analogous to polynomial time, we had the class P, which indicated the set of all computational problems which can be decided in polynomial time. So which is n power k time by some deterministic Turing machine, right? So we had P, which was union of d time n power k. Analogously, we have P space. It is a set of all computational problems that can be decided in polynomial space, right? So this is equivalent to, or this is analogous to, not equivalent, analogous to P, right? So these are some of the common complexity classes, and most likely we'll not be seeing too many more complexity classes which classify problems in terms of space usage, because of the time that we have. We have just this week 12 to cover space complexity classes, right? But maybe we'll see one or two more. Okay, so the classes that we'll see is N, NL, and P space, right? So now, having explained all of this, now let us move to. So we have defined things in terms of time, things in terms of space, deterministic, non-deterministic, etc. So now let us see how these classes compare against each other, right? So many of them are simple, but some of them require some amount of cleverness, right? So we are going to see some relations between complexity classes based on time, space, etc., right? So first thing is that d space fn, right, for any fn, right, for any function, d space of fn is contained in n space of fn. Right? We saw something similar in time. D time fn is contained in n time fn, because a non-deterministic Turing machine can just act like a deterministic Turing machine. In other words, a deterministic Turing machine can be viewed as a non-deterministic Turing machine that does not use all the options. So d space fn is contained in n space fn, right? It's straightforward, right? And this implies that if you set fn equal to log n, this implies that L is contained in NL, right? Right? But one may ask at this point, is it a proper containment? The answer is we don't know, right? Now next thing is relates deterministic time and deterministic space, right? So suppose there is a language that requires fn time or OFN time to decide. We are saying that it can also be decided in OFN space. This is also fairly simple. The OFN time Turing machine, the Turing machine that decides in OFN time, that runs only for Fn time. So which means that Turing machine cannot use more space than Fn space, because if you give 100 time steps, the head can only move 100 cells, because each time step only one cell, right? So that the space usage is not going to be more than the time, right? So the Turing machine that decides the language in Fn time or OFN time is already space limited with OFN space, right? So the maximum space used by the same Turing machine is OFN. Hence, d time Fn is contained in d space Fn. So this is also fairly straightforward. Now the next thing, so instead of d time Fn, one may ask, what if we had a non-deterministic time Turing machine? Right? So then we cannot use the same idea, because we want to simulate a non-deterministic time-bounded Turing machine with a deterministic space-bounded Turing machine, right? So we cannot use the same idea. So what we will do is something that we have already seen. If you remember, we simulated non-deterministic time-bounded Turing machine by deterministic time-bounded Turing machine, right? In lecture 31, while studying computability, we saw the simulation, and lecture 47, when we studied time complexity, we actually assessed or calculated how much time it takes, right? So if you remember, we said that anything that can be done in non-deterministic time f requires deterministic time 2 power order f or something like that, right? So let us just revisit that. So the same approach works here, is what I want to say, right? So what was the approach? The approach was to, like, you have a computation tree, right? So we know that it runs in n time, non-deterministic time Fn, which means all computational paths get completed in order Fn time, and then we want to identify if there is some computation paths, some computation path that leads to accept. So maybe I don't know. Right, some computation path that leads to accept. So out from the computation tree, we are looking for such a path. So what we can do is we can just go through all the paths in the breadth first search manner, right? So if you remember, we discussed this earlier. We said that each path will be labeled based on the based on which branch it takes at each configuration. So here it will be 1, here it will be 2, and then maybe again 2, I don't know, here it is 3, whatever. So this path will be labeled 1, 2, 2, 3 something, right? So you have a counter that can track which computation path it is, and we basically keep cycling through the counter, right? And the number of symbols in each of these positions will be upper bounded by the branching factor, right? So there will be some branching factor b, which is the maximum number of children any configuration can have, right? And so that will be the number of symbols each position, each position this counter can take, right? So it's a b bit counter or b symbol counter, or the base of this counter is the capital B, and but then the length of the counter is no more than OFN, right? Because that is the height of the computation tree, right? So in fact, all of this we discussed in lecture 31. So maybe you can refer back to those lectures. But just that we didn't look at it in terms of any time complexity or space complexity, right? So each computation path can be encoded by a string of length OFN, right? That's what I said, the counter, and we keep track of these strings. And so we have two things. One is that counter, right? We have this counter that keeps track of the computation paths, and then we need to simulate the non-deterministic Turing machine. So suppose you fixed a number, let's say 1, 2, 2, 3 something, and then for that specific string, right? Say for the string 1, 2, 2, 3 something, we want to simulate the NTM. So there is no non-determinism there. The counter is already there. Based on the counter, we decide the choices, right? And this will require OFN space, because we are just running an OFN time Turing machine. So again, OFN time will run in OFN space also. So the OFN length counter is the first thing, and then for the simulation itself we need OFN space, but that is for one specific counter, one specific string output by the counter. Now when we update to the next string, we don't need to keep track of what we did with the earlier string. We can just do it afresh. We can reuse the space, right? This is an interesting thing with the space. We can keep reusing it. We don't need to preserve what was done earlier, right? We don't need to preserve everything that was done earlier. We maybe only need to store a few bits of information. In this case, we just need to store whether we have found an accepting earlier or not. In fact, if we found an accepting, we would just close the entire simulation. Otherwise, we would just continue, right? So we have two things. One is OFN length counter, and each simulation taking OFN space. So overall space required is OFN, right? So while it's a deterministic space bounded Turing machine that takes OFN space, right? Which is what we have said here. N time Fn can be simulated by D space Fn, right? So this is another result. So in fact, this is similar to the way we showed that SAT is in D space N, right? So basically, we are taking it's kind of the same thing, but set in a more general setting. Right? So there also we explored all the 2 power n possible choices and said that it takes only an n bit counter and constant space. Here we are saying it takes OFN bit counter and OFN space, right? So n time Fn can be simulated in D space Fn. Right? Next thing, we change the roles. Suppose something, so far both the results or two things we have said is D time simulating in D space and n time simulating in D space. Now let's see how much time it takes to simulate a space bounded machine, right? Suppose we have a D space machine that runs in OFN space, and how much time does it take to simulate, right? And what we say is that it takes 2 power OFN time. We also need an assumption here. The assumption is Fn is at least log n. This is actually an important assumption, and usually this many statements in space complexity will be accompanied with this assumption. In a way, the point is that we need it is not really meaningful to measure D space Fn if Fn is smaller than log n. Like if Fn is little of log n, D space of Fn does not really make much sense, because at least one thing that we may be interested in doing is to keep track of the indices as we scan the input, right? So the input length doesn't matter, it doesn't count. But let's say we need to look at the 10th symbol of the input or nth symbol of the input or n minus 10th symbol. Then we need to have a counter to keep track of where I am, right? The Turing machine doesn't automatically give us a counter. So we need to have a counter. So the counter will range from 1 to n, which means it needs log n bits to store such a counter. So I am saying why this assumption that Fn is at least log n is not it's a reasonable assumption, because below log n we cannot meaningfully do something, right? And why we need it, so this is why it is a meaningful assumption. It's not really we are not losing anything by restricting ourselves to this assumption, and why we need it we'll see in this proof, right? So this is for most meaningful space bounded machines, this doesn't really hurt, this assumption. Okay, so D space of Fn means there is an input tape and there is a work tape, right? Let's assume that it is an accept reject, it's a decision Turing machine, and the space used in the work tape is Fn, right? That's what this means, D space of Fn, right? And let's see how many configurations. So one thing that we can do is to run the space bounded Turing machine, and let's see, it's a deterministic Turing machine, the left side also deterministic, right side also deterministic, right? And we just run that space bounded Turing machine and see how much time it takes. And what we are going to do is that is going to be good enough. Just that we are going to limit the running of the time bounded Turing machine to this much time, and we are going to say that we will always get a decision, right? So we just run the same machine, and if we measure the time taken, it is going to be at most 2 power OFN. If it doesn't conclude by that, we can stop the computation and reject the input, right? So let's see why that is the case. So the claim is that if something runs in D space OFN, the time taken is 2 power OFN, right? So let's see why that is the case. So the number of configurations of the space bounded Turing machine, let's see what it is, right? So we have multiple things which constitute the configuration. One is the head positions. So there are head positions which is in the input tape and the work tape. So this is because of head positions. So the input tape, the head could be in anywhere from n positions, right? The n is the length of the input, and the work tape, the length is fn. So the head position can be anything from 1 to fn. So that there could be fn possibilities for the head position of the work tape and n possibilities for the head position of the input tape. And what the input tape contents are fixed for a specific input, right? So that there is no scope of changing. What is the number of possible contents of the work tape? So contents of the work tape, it is going to be gamma power fn. So contents of work tape, it's going to be size of gamma power fn, where gamma is the tape alphabet, right? So contents of the work tape, because there are fn cells and each of these cells can have any tape alphabet, tape symbol there. So it's gamma power fn. And then we have the state, the number of states, which is q, right? So these are the things that comprise of the configuration. Now if you just see this, this we can simplify as 2 power some constant times fn, right? So we can see gamma as 2 power some constant, and we have n fn here and q here, it's the same thing. But then all of these things are dominated by the 2 power constant fn term, n fn q. So q is a constant, n is linear term, and fn is going to be, we know that fn is at least log n. So it is going to be dominated by 2 power fn, right? So what we can do is we can easily absorb all this into the exponent term. So we can replace it with 2 power another constant fn. So 2 power c2 fn, right? But it's just another constant, which we can say 2 power o fn, right? So now the number of configurations of the space bounded Turing machine is 2 power o fn. Now number of configurations is 2 power o fn means it has to terminate in 2 power o fn steps, right? If it does not terminate in 2 power o fn steps, that means it is repeating some configuration, which means it will just get stuck in some loop, right? So if you run in that time, and if we accept, fine, we accept. If we reject, fine, we reject. But if it does not terminate in 2 power fn steps, 2 power o fn steps, that means we are stuck in some loop, because there are only, let's say there are only 100 configurations, and if you have run 110 steps, right, and we have still not accepted or rejected, means that some configuration is repeating, and it's just going to repeat again. We are just basically stuck in a loop, right? So there is no point of just going through the loop over and over again. We may just as well accept that it is stuck in a loop and reject the input, right? So we just run the D space machine for and limit the running by this many steps, 2 power o fn steps. If it accepts, we accept. If it does not accept, in that much time we reject. So the main key idea here is that we bounded the thing in terms of bounded the number of configurations, and that gave, so it is an exponential in the time, in the space complexity, and that gave us a time bound. Okay, and obviously this gives us a corollary. So if fn is set to be log n, right, if fn is set to equal log n, we get that, right? If we set fn to be log n, we get that d space of log n is obviously L, and d time of 2 power constant times log n is obviously P, right? Or some polynomial. So we can say it is contained in P. So L is contained in P, right? So this is something that maybe not too surprising, right? Something that runs in log space will not take more time than polynomial time, right? So here we compared the deterministic space and how much time it takes to run a deterministic space Turing machine. Next thing is we will move to a non-deterministic space Turing machine, right? So we move to non-deterministic space bounded Turing machine. Again we use the same assumption that fn is at least log n. one point, we actually use this assumption over here, right? We use this assumption over here, because if we don't have this assumption, we cannot assume that this n_fn is dominated by 2 power c fn, right? Because you're assuming that n is dominated by 2 power c fn, so we have to assume that fn is at least log n, otherwise we cannot do that. That is where this assumption actually plays a role in this proof, to move from basically this inequality. Okay, so same, in a similar way, it will play the same role here as well. So now we are saying that instead of deterministic space bounded Turing machine, we are dealing with a non-deterministic space bounded Turing machine, but the result is that it takes the same amount of time. It can be simulated in d time 2 power O fn, right? D time 2 power O fn. So this right hand side is the same, but left hand side has been replaced by n space. We cannot use the same simulation that we did here, where we just ran the d space Turing machine, because d space Turing machine is just deterministic. But non-deterministic space bounded Turing machine, there could be multiple approaches. So now we cannot run it just like that, because running it itself requires us to explore many computation paths, etc. Right? And if there is a branching factor of b, then if you do some kind of like all paths, if you try to explore, that may result in some kind of double exponential thing, like b power 2 power O fn configurations, right? Because we have a tree that is of height fn, right? We have 2 power O fn configuration, so the tree could be as big as 2 power O fn size. That many different configurations, but then each configuration can have as many as b children, right? So this could be as bad as this. So we don't really use this kind of a straightforward approach. The thing is that the total number of configurations is bounded, right? So we already saw that the total number of configurations in the case of a d space Turing machine is bounded by 2 power O fn, and n space also is the same bound, because the configuration doesn't really depend on whether it is deterministic or not deterministic, right? It is just contents of the work tape, head positions and state, right? So the number of configurations is going to be 2 power O fn, right? Or at most 2 power O fn, right? So the point is that many of these like b power 2 power and things, the configurations, they are like duplicate, like it may be the same configuration may be appearing in multiple computation paths. So we don't need to duplicate the effort. Instead, we can just look at the entire tree, entire set of configurations as a single directed tree, right? So we have the C start, which is the starting configuration of the starting configuration. Just hold on. Of, so did I say NTM on input, right? So whatever input it is, once we decide the input, it's the starting configuration is fixed, right? And then how many valid successors does it have? So some successors, and they will have more successors and so on. So we'll get some kind of a directed graph, which is a configuration graph, right? And we just want to know whether there is some way to reach the accepting configuration from the starting configuration, right? But then there is another problem here. The problem is that there could be multiple accept configurations, because the accept state is unique, but the tape contents could be different. But what we can do is modify the Turing machine such that whenever it accepts, it erases the tape contents, right? So erases the tape contents and bring the head back to the left end, right? Which means there is only a single accept configuration, right? We can assume there is a single accept config, right? We may assume there is a single accept config. So now in the computation, in the configuration graph, right? So you start from the, so it's a directed graph where you have an edge, right? You have an edge. If there is a valid if this configuration is a valid or this configuration is a valid successor of the previous configuration. So you have a directed edge from I to j if j is a valid successor of I, right? And that is easily checked by the rules of the non-deterministic Turing machine, right? So we can build this configuration graph. Another point is that we don't need to explicitly build it. We can kind of have this idea in mind and just build it as we like guess or make the next step as we go along, right? We can kind of on the fly check whether the edge is there or not. All we need is access to the information whether there is an edge from I to j, and this can be done on the fly. We don't need to like set up an adjacency matrix because that's again going to be too much space and too much time, right? Right. So we don't need to do that. So, but what we are right. So, in fact, in this case, we can actually build the configuration graph and build the adjacency matrix also, because anyway the running time that we are using is 2 power OFN, right? So we can build this configuration graph and we need to check whether there is a path from start to accept. So we can use any traversal algorithm, right? We can just use breadth first search or depth first search, which runs in linear time in the size of the graph. So v plus e time, which is at upper bounded by v square time, which and we know the number of configurations is 2 power OFN, right? That's something which we said here as well as we said here, right? So that implies that the running time of the BFS is also going to be 2 power OFN. The square gets absorbed in the O here, right? So it's just asymptotics, and even this O is unnecessary. So the running time is 2 power OFN, right? So what we have shown is that an n-space Turing machine which runs in OFN space can be simulated in d time 2 power OFN, right? So again, this even though it's a non-deterministic space bounded machine, it took the same time as a deterministic space bounded Turing machine, right? So this is also d time 2 power OFN, this is also d time 2 power OFN, right? And this implies that by setting Fn to be log n, we get that we set Fn to be log n, we get that n space OFN or n space of Fn is NL, right? Sorry, n space of log n is NL, and d time of 2 power O log n is basically d time of n power some constant, which is polynomial time. So this shows that NL is contained in P, right? So yeah, I think that is that's what I want to say in this lecture, lecture number 57. So we introduce space complexity, right, which is the maximum space taken by an input of any length, and in the case of a non-deterministic Turing machine, it's the maximum space used by any branch of computation on any input of the same length. And then we said that the standard model of computation, standard Turing machine model, may not be good for measuring the space because it forces the space requirement to be always at least n. So we considered or we structured another model where we have the input separated from the work tape, where the input is read only and you cannot work on the input tape, and the space that counts is only the space in the work tape. Now with this model we can make meaningful statements like this problem can be decided in O log n space, right? So then we said some statements. So so we defined some complexity classes like L, NL and log space. Sorry, L, NL and P space. So L is log space, NL is non-deterministic log space, and P space is polynomial space. And we saw some relations. First is that D space Fn is contained in N space Fn. D time Fn is contained in D space Fn. So one consequence of this is that so P is contained in P space, right? If polynomial time and polynomial space, right? Yes, and then we saw that non-deterministic time is also contained in log space. The same space. So this shows that even NP is contained in P space, right? That's what this shows, right? And then we saw how space-bounded Turing machines can be simulated by time-bounded Turing machines. So D space of Fn is contained in D time 2 power O Fn, and N space Fn is contained in D time, is also contained in D time 2 power O Fn. So by setting Fn to be log n, we get that L is contained in P and even NL is contained in P, right. So that is some the introduction to what is space complexity, and also some relations between how these space complexity classes relate with each other as well as with time bounded complexity classes, right. And in the next lecture we will see something called so just like we had NP completeness, we will see a notion of completeness, but it will be NL completeness, not P space but NL completeness. Yeah, so that's what we will see in the next lecture. As far as lecture number 57 is concerned, that's all from me, and see you in the next lecture. Thank you.